Hi, welcome to the hydraulics lab this week. So today is the lab 4, as you know. So if you open your lab manual, then you can see what is the name of our lab today: flow over hydraulic structure. So first of all, I want to talk about a little bit hydraulic structure. So what is hydraulic structure? Hydraulic structure is the kind of structure placed across the canal or open channel, which is very helpful to divert the water or the control the flow. Okay, so one of the purpose is to measure discharge using the hydraulic structure. Okay, so today I'm gonna show you different type of structure, like as you know from before, that sluice gate, weir. So sluice gate is a hydraulic structure. So weir is a hydraulic structure. Say for example dam, if we want to store the water, so that is a hydraulic structure. For maybe some of you already know the Hoover Dam, right? That is basically hydraulic structure. Spillway is also a hydraulic structure. Culvert is a hydraulic structure, and so on. And today we'll use only one structure. So of course we have very limited time, so I cannot show you the whole kind of structure, but I'm gonna show you one kind of structure, that is weir. So if you look at your lab manual, the purpose of the experiment is to determine the theoretical discharge of the weir. So weir can be many types. Okay, so but for this experiment we will use the sharp crested weir and the broad crested weir. I'm gonna show you what is sharp crested weir and broad crested weir looks like in a while. So, and what is the purpose? So purpose is to measure discharge. Now the question is, how can we measure discharge? We can simply measure discharge like volume by time, right? So this is very common practice in the lab. So how can we measure discharge? Volume by time. If we know the volume and we record the time, then we'll get the discharge. But in the real life it is almost impossible. So if you have very large canal, you cannot store the volume of water and measure the discharge. So that's why we need to help of help of any hydraulic structure, so that we can measure indirectly the how much flow rate in a canal or in any open channel. Okay, so so that is an indirect measurement. Okay, so if we know the actual discharge, and if we measure the indirect discharge based on some formula or theoretical discharge, then so if you know the coefficient of discharge, what is coefficient of discharge? So how much variation in actual discharge and the theoretical discharge. Okay, so if you know the coefficient of discharge CD, okay, for any structure, if you place across that structure, you can simply measure the actual discharge. So I'm going to show you how. So first of all, let's see how does it looks like for sharp crested weir and the broad crested weir. Okay, all right, so this is our purpose. So to measure theoretical discharge and measure actual discharge, so experimental discharge or actual discharge, which is volume by time, right? So this is kind of theoretical discharge. We need some formula, right? So we need two formula for sharp crested weir and the broad crested weir, and we have to also measure the actual discharge, which is volume by time, right? So that we can compare. So let's go to the second slide. So this is basically sharp crested weir. Can you see the weir? So it's basically, you know, this is our sharp crested weir. So flow profile is looks like this. So how can we measure the theoretical discharge using this? So if you look at here from this is the height of the weir. Okay, so from the top, so this height is basically, you know, 75 millimeter. Okay, so this is the 75 millimeter, and from the top of the weir to the top of the free surface, so this is called the head of water. Okay, and B, so you can see this is the formula to measure the theoretical discharge using the sharp crested weir. Okay, so that is 2 by 3 square root of twice G B. So B is equal to 77 millimeter. And what is H? H is the height or head, which is from the top of the weir to the free surface of the water. Okay, all right, so this is basically the head. So if you know the head, you can plug this head value and calculate the theoretical discharge. Okay, so this is the sharp crested weir. Why this is called the sharp crested weir? So sharp crested weir because if you look at the crest of the weir, this is very thin, like this. Okay, so the height of the weir is 75 and the width of the weir is 77. Okay, 77 millimeter, just like the last experiment, you know. Okay, so this is called the flow profile. So if you already started the gradually varied flow in the class, then you understand the flow profile, right? So M1, M2 and so on. Okay, so this is the sharp crested weir. Now I'm going to show you what is broad crested weir looks like. So look at this slide. This is the broad crested weir. Okay, so this weir is crest is very, you know, long. Okay, so if you look at here, this crest is very long. Okay, so why this is called broad crested weir? This crest is broad. Okay, and simply, and head loss here is very high. You know why? Because there are more free surface, so head loss is very high. So if you look at this shape over the weir, it almost looks like a trapezium, right? So at the centroid of the trapezium, just like here, if you can expect the critical flow, you know. So hydraulic structure, upstream of hydraulic structure, we have subcritical, right? And downstream we have supercritical. So in between there is a section that is called the critical flow. Similar like okay, so here is the broad crested weir, and this is the subcritical depth and the supercritical depth. So in between there is a section which is called the critical depth. So why the location of the critical depth can be usually determined by, you know, the centroid of this area. So if this is like trapezium and kind of here is our centroid, right? So this is called the critical depth. So based on some assumption, we can easily derive this formula. So if you look at your lab manual, then you can clearly see how can we derive this formula. So this is the formula basically. So 2 by 3 to the power 3 by 2, so square root of G B. So B is, which is basically 77, so width of the flume, you know, and H1 is basically the head. What is head? From the top of the weir to the free surface. So if you know the head, you can easily calculate the theoretical discharge. Okay, so for the sharp crested and the broad crested, so we have two different formula, right? So what I'm gonna do, I'm gonna provide the data for the head and the corresponding time. Why do we need time? We have to calculate the actual discharge, which is volume by time. So I'll provide the volume and the time for your 5 observation. Okay, and then you can easily calculate your theoretical discharge and the actual discharge, then you can compare. Okay, so what kind of data do we need? Let's see first what kind of data do we need. Okay, so this is your lab manual, and if you go down, so here is the flow profile kind of for the sharp crested weir. So, and this is the experimental setup, and this is our assumption. Based on this assumption, we can derive the formula for the theoretical discharge for sharp crested weir, and this is called the CD. What is CD? CD is basically actual discharge divided by theoretical discharge. So this is the ratio. So if you know the CD of any weir, then you can place that weir in real open channel or any real canal, then you can easily use the formula, right? Use the measure the head, calculate theoretical discharge, and you have already the CD, so you can compute the actual discharge, because in real life you don't have chance to collect the volume and collect the time, right? Okay, so that's why we need hydraulic structure to measure the discharge. So this is the derivation for the broad crested weir. So this is your raw data. You need time and the head for both. So what we're gonna do, I'm gonna provide you the same head data for both weir, sharp crested and broad crested. Then you can calculate the CD for the both and to see how much variation for the sharp crested and the broad crested weir. Okay, so now I'm gonna show you how can we collect the data in the lab. Okay, all right, so let's come with me to see how can we calculate, how can we collect the data. Okay guys, so this is our lab 4. I'm gonna show you the hydraulic structure. Do you know what is this? This is called the sharp crested weir. So last year some high school kids came here and I asked them what is this. They said the block. So of course this is block, but this depends on the purpose of the flow. So when flow over this structure, then we call it weir, and if the flow is under the structure, then we call it sluice gate. So for the lab 4, we have to see how the flow profile looks like and how can we compute discharge based on this hydraulic structure. So we have so many hydraulic structure. So for example, you have already seen the sluice gate. This is also a hydraulic structure, and this one is called weir, although it depends on the purpose. So this is called also weir. So you can see the similarity, weir. So this is called sharp crested weir and this is called the broad crested weir. So what is the purpose of weir? Can you measure discharge, amount of discharge in the real field? No. We don't have the big size of pond to collect the water and then time. We cannot do that, right? So we have to use indirect method to measure discharge. So weir can be that method. Okay. So all right. So for the lab 4, I'm gonna remove all of the structure from this flume. So right now my sluice gate is open and weir is also open. There is no structure right now. So if I turn on my pump, what will be the flow? It's called uniform flow, right? So why uniform? Because the depth doesn't change with respect to the cross section. So that is called uniform flow. But if I place this hydraulic structure across this flume, then we can see the flow profile. Okay, let me put the sharp crested weir first. So if I put this way, then how does the flow profile looks like? Of course, I am pretty sure you have read the gradually varied flow in the class. Okay, let's see how does the flow profile looks like. Okay. So this is hydraulic structure. At the upstream, you can see this is subcritical flow, and at the downstream we have supercritical flow. It's interesting, right? And when we have sharp crested weir, then there is a zone called there is no water and no air. So this is name is NAPPE, NAPPE. So why this has happened? Because our crest is very sharp. So what is the height of the structure? This is, you can see, 75 millimeter. And what is the width? That is 77 millimeters. So width is 77 and the depth is 75. So where is the location of critical flow? Somewhere here. If you look at from the top, then you can see there is a streamline is converging and then diverging. So somewhere here is our critical depth. Okay, so here is the head. Head is basically when you have 100 millimeter, so 100 minus 75 will be your H value. So that is called the head, and below this head we don't have the flow. So this zone is called the dead water zone. Okay, so we have head, we have discharge. How can we measure discharge? Again, volume by time. Okay, now we have the formula. By using this head we can measure discharge also based on formula. So that is the theoretical discharge, and we have experimental discharge, volume by time. Then we can calibrate to see what is the coefficient of discharge, which is CD, basically QA by QT, right? Okay, so that's all about the sharp crested weir. Now I am going to show you how the flow profile looks like for the broad crested weir. Okay, now I am placing the broad crested weir here, so you can see what is the difference. Okay, so this is broad crested weir. Why this edge is round? Because we want to make sure there will be no NAPPE. Okay, so let me start. Okay, so again the height of this weir is same, 75, and this is our head. So you can see there is no NAPPE here, so that's why the edge is round. So head loss is little bit higher here because we have so much surface area here. And if you look at from the top, you can easily see that the streamline is converging and then diverging. So if I move my finger here, so if you look at here, this is trapezium, right? So this is trapezium. At the centroid of the trapezium, so this depth is pretty close to your critical depth. Okay, so after the structure we have supercritical, and before the structure we have subcritical. So streamline is converging and then diverging. So here this depth is called the critical depth. Okay, so I will provide you the H value so that you can calculate your discharge, and I will provide you the experimental time and volume so that you can measure experimental discharge also. Then you can check. So what is the coefficient of discharge for both the sharp crested and the broad crested, then discuss based on that. Okay, so that's all about lab 4. So hope you enjoy. Alright guys, now you have all of this data for table 1 and table 2, right? So which is called the raw data for table 1 and table 2. So you have time and the head. So here we are comparing for the same data, right? So you have same time, same head for the sharp and broad crested weir, and this is your data. You can see so width of the weir for both weir, width of the weir is 77 millimeter, which is basically the internal, internal width of the flume or external width of the weir. Okay, and height is basically 75. So first of all, so what is head? So head is basically you take the reading for the upstream height of the water and subtract from that height 77 subtract 77 from that height, you will get the head, right? Head in millimeters. So if you plug this head, then you can complete this table. So this table is for the sharp crested weir and the broad crested weir. So volume, what is that volume? Volume is basically 15 liters. So we have taken time for 15 liter volume, so you have to convert this 15 liter to millimeter cube, right? Just like the last experiment, and then you have to complete this table. So volume time discharge head is basically same for both table, right? But what is different? The theoretical discharge is different. That's why CD is different. So then you can draw two graphs. One is for sharp crested and one is for broad crested. What is that two graph? Actual discharge, which is volume by time, and the theoretical discharge, which is based on the formula. That which formula? These two formula for sharp crested and the broad crested. Okay, and calculate the CD and discuss how is different for sharp crested and the broad crested weir and why this is useful. So I'm going to see what kind of discussion you have, and I'm going to grade on based on that. Okay, and don't forget to answer the lab questions. So if you take a look on the lab question, so what are the assumptions made in deriving this equation? So if you look at your lab manual carefully, then you should be able to answer this question and discuss the observation of nappy. Okay, so if you look at the profile for the sharp crested weir, you know there is a zone called, so this is a vacuum, right? So there is no water, no air inside this zone. Okay, so this is called the nappy. Okay, so to avoid this nappy, so the edge of this broad crested weir is a little bit round, you know, to avoid the nappy. Okay, so look at your lab manual and you will learn more about nappy. Okay, then plot the QA versus QT, determine the value of CD for the sharp crested weir, same thing for broad crested weir. And question number 4 is basically, so discuss the advantage and disadvantage of both weir. Okay, and the use of broad crested weir, why do you want to use this and that weir. So that's all for question lab 4. Okay, so hopefully see you next week with lab 5. So this lab is basically the last lab for open channel, not the last lab for hydraulics. Okay, so last lab for open channel. I will upload this and I will open a assignment for you, lab 4, and till then, stay healthy and stay safe.